All right. All right. Hello, everyone. Welcome. This is our fourth meeting of the Compute Over Data Working Group. Very glad to have everyone who's joining in live. And we're very fortunate today to have the Ceramic team who's going to give us a rundown of their tech stack, and then also the Bacalhau project after them. And so Joel, we'll let you lead it off first. And thank you for joining. And we're looking forward to whatever content you'd like to share.
Great, thank you. Hi, everyone. I'm Joel, technical co-founder at Ceramic. With me today, I have Spencer and maybe Sergey if he joins later. So we have a lot of people who can answer questions today if we get to them. Yeah, so I kind of wanted to jump right in. I'm going to share like a kind of intro, high-level overview to Ceramic, then dive into some of the things that I think might be a little bit more relevant to this group. Right, so do you see my slideshow right now?
Looks good.
Perfect, okay. So intro to Ceramic. We see Ceramic as kind of like an open graph for Web3 data. You can kind of think of it as like this open knowledge graph of the internet. It's alive, meaning that anyone can update it and kind of like add things to it. And it's like relational, you have relationships between different things. And from this, you can kind of get this emergent web of trust. And we can start to like make sense of the world, because now the internet is not only something that's presented to us by web pages, but we can actually inspect the underlying contributions, how people interacted. And so some of the kind of thinking that came into like being important when building Ceramic is that we wanted to have the ability for applications to share data across themselves, so like across applications and across organizations. We want people to be able to like optimize their workflows for their applications. We want data in the network to be composable, meaning that if there are two different applications out there and I see some useful data in both of them, I want to be able to take those, put them into my application, and just run with it, kind of use that. And when I make updates in my application, those should propagate to the other application. So the data kind of is composable, and that's like interoperable and kind of there and is unlocked into like any particular app. And so with this, we can of course like increase like innovation in the Web3 space more, similar to like how we did with like the blockchain for like financial sort of things. We want to be able to like do that with data. And to do this, we need things to have authenticity. We want the network generally to be censorship resistant. We want every action in the network to be authenticated. We want audit trails that we can audit after the fact. And if we have this, we can actually let authors of different sorts of the different parts of this kind of decentralized knowledge graph to build reputation. And so why don't we actually use a blockchain to do this? Because it has all these properties, right? Well, there's some problems with blockchains. And it boils down pretty much to blockchains favor strong consistency. This is great because it prevents double spend, which means that we can manage funds. It means that we can have public goods funding. We can have NFTs. But the kind of main limitation is that blockchains are limited in throughput by the block producer, basically the node that is producing the current block and the next block and so on. And that can only be so big. And you can't really like build a Twitter or Facebook on like a strong consistency model where everything goes through like one node. So different people have approached have different approaches to scaling blockchains for data. Some do like the bigger block approach, so like Solana, Celestia, Arweave. They have like different ways of making sure, like, or convincing themselves that like, hey, this big block producer is fine because we have this kind of validation methods for it. And so, but you're still limited by the throughput of the block producer. Then you have like the sort of proof of storage approach, which Filecoin uses, which SIA and Storj also uses. And here you can have big blobs of data that you publish, and then you have some kind of agreement between two different nodes or a set of nodes that, hey, this data will be stored and be available. But you're still kind of limited by the throughput of the block, because you can, if you have like 100 million users, they can't all make one transaction each to like, hey, here's my new data. And generally, like, a user only has like a small piece of data that they're updating, not a huge blob. So if you want to build a system where you have like a lot of participants, you either have to have like some centralized aggregator, or you kind of have the limitation of the block here. And so can we do something better? Can we have something that's decentralized and eventually consistent? So we want to have parallel data execution, or data production rather. And we think we can achieve this through like having audit trails that are kind of independently verifiable. And we still want some properties like data composability, that data shouldn't be like kind of locked to the different places where it's at. And this would generally, of course, only work for non-financial data, because for financial data, you want strong consistency. And so imagine if you have like a set of event streams that are verifiable, you could have something that looks like this. You have the different colors here represent like different subsets of the network. And so your database might care about like some particular subset here, or basically like shard the network in this way. So you have like the different subsets of shards. But someone building a different application might want to like have a different topology of like how they build their indexes. So same data, but like different configuration. And you can actually achieve this if you have independently verifiable event streams. But if you have something like hierarchical consensus, you still kind of like produce the Filecoin uses, you still produce like blocks, and they like the data is kind of in a particular shard, and then you would need to move it. But here you can actually produce the data independently, and then you can build kind of like specific consensus over different places. So that's why in Ceramic, we have separated 2 layers essentially, or 3 layers if you think about the kind of user experience. So the base layer, we have an event streaming protocol. On top of that, we have a database protocol. And on top of that, we kind of have this nice GraphQL APIs. And the kind of system we're building for this is called ComposeDB. So I'll kind of quickly go into ComposeDB. I'm kind of gonna rush through this because I think most relevant for this call is the event streaming layer. So yeah, ComposeDB allows nodes to create indexes for the data that they care about. Data models is basically a way to specify a subset of data that conforms to some semantically meaningful schema. And yeah, nodes choose which models they index. And you can query across kind of like linked models. So a data model just describes how data looks like, and any user in the network can write data to this model. They're creating using the GraphQL schema definition language. Of course, use GraphQL to query over them. And these data models are discoverable and composable. So I can take 2 existing data models, pull them into my application, and build something new. And roughly, this is kind of what it would look like to define a model. This is kind of a little bit outdated, so don't use this in your code. But here you have a model for a proposal. So imagine like a DAO proposal. It has an author, it has text, and so this author here is like proven cryptographically by this document account kind of tag, and then the text is just some string that the user puts. Then you have a comment, and same thing here. There's an author, there's a text, but we also have a proposal ID, which references kind of like the ID of a particular instance of a proposal. And then you can kind of see that we have a comments relation here in the proposal model. So you're going to have this kind of relationship that allows you to query, hey, for this proposal, give me all of the models. And so you can kind of imagine how this generalizes to a graph of data models. Anyway, so that's the database system we're building on top of Ceramic. If you're curious about that, please reach out, but that's not what this is about. So event streaming. Here I want to like slow down a little bit and allow us to dig a little bit deeper. If you at any point have any questions, please feel free to interrupt me, and we'll go through that. So first of all, event streams in Ceramic are completely independently verifiable, meaning that I can synchronize one event stream in the network, verify it, and be sure of its integrity without having to verify any of the other data in the network. So this is kind of fundamentally different from a blockchain where I need to like synchronize all the state of all smart contracts in the network. Here you synchronize the state of like one event stream, and you can verify that. Excuse me. Then we use decentralized identifiers, DIDs, for authentication. And we've built a system that allows us to use essentially like any blockchain wallet in principle to write into Ceramic. And I'll go into a little bit more what that looks like. We have a peer-to-peer network for synchronizing events, or synchronizing the event stream in general. And we sort of like have a prototype for like how this works right now. In the future, we want to build something that's like a little bit more scalable. So that looks like some sort of like custom libp2p protocol. And I'm happy to like dive into that if anyone has questions about that. And then all data is soulbound, meaning that data is authored by a particular account, and there's no way to like transfer the data, like transfer ownership essentially. So like the data is with you, and you can't like trade the data in the sense of like an NFT. If you want to trade something, use the blockchain and use NFTs for particular things, or tokens. So an event stream looks roughly like this. This is kind of like the high level view. And of course, like if you dig into particulars here, there's more nuance. But essentially like this. So you have a different events, or the event stream is made of events. And first you have a genesis event that essentially creates the stream. And we have something called stream ID. The stream ID is just like an identifier for the stream. And that's based on the CID of the genesis event. Then there are two types of events in addition to the genesis event. One is an anchor event, and one is a signed event. So an anchor event is essentially a timestamp that utilizes a blockchain, in this case Ethereum, to provide a cryptographically like verifiable, trustless timestamp that, hey, this previous event was published, did exist at least at this point in time. And so we have a system for like how we reference that and how we batch that into a Merkle tree, so we can actually like anchor not only one stream with one transaction, which would be like very unscalable, but actually make one on-chain transaction and anchor a large amount of events at the same time. Then we have signed events, and the signed events includes a signature, basically proving that, hey, I'm making an update, or I'm adding an event to the stream, and I'm actually like authorized to do so. So the Genesis event specifies the account, the DID, that's allowed to make updates to this event stream. And the signed event basically like says, hey, here's a new event to this event stream, and here's a proof that I'm allowed to make an update to this event stream. So we're using the IPLD tag Jose to store the signature, and the signature is authored by a particular DID. So this whole event log fits very neatly into the IPLD data model. Yeah, and then you can use like add more signed events. You can add new kind of timestamp anchor events and so on. You can keep like growing this event log, and it's all like hash linked together from Genesis to like the latest event. And so right now in Ceramic we support kind of like only one canonical branch of history. In the future we want to like allow us to diverge and converge on the log, because you might have like nodes that are not completely in sync, and we don't want to lose data. Yeah, so that's kind of high level the data structure, and diving into like how the authentication works. Is that generally, if you think about distribution of public keys in the world right now, you have essentially like Ethereum wallets and Solana wallets that have like really big penetration in the market of like just providing public key infrastructure. And we want to leverage that, right? We don't want to have to build a new wallet for all different kinds of sort of things. So in this case, you have a wallet that holds a public private key pair, say an Ethereum address. From an Ethereum address, we can create a DID PKH I'm using Ethereum here as just an example. This would work for like any sort of blockchain wallets that has like a public-private key pair. Did PKH stands for public key hash. So if you know an Ethereum address, it's basically a hash of a public key. And the did PKH basically like says Ethereum address plus which network it's on, and now it's a DID. And then there's a resource in Ceramic. In the case of Ceramic, it's an event stream. And so in the Genesis event, it's specified that, hey, this particular did PKH controls this resource. Okay, great. So now if I want to update this resource, I would in theory just need to produce a signature by this wallet. But if you think about like the user experience, you don't generally want to have to sign a message in MetaMask every time you're making an update, especially if it's like a social media app, you just want to make a comment, or like it's a DAO proposal, like you don't want to like always have to pop up a MetaMask pop-up. And so to mitigate that, we're using something called object capabilities. So we basically leverage sign-in with Ethereum for Ethereum. There's a similar standard being built for Solana and can be extended to like different blockchains as well. Basically, you generate a session key, which is a DID key in the browser. Then you have a message, or you generate a message that includes the public key of the session key and includes the kind of identifier of the resource, a stream ID for Ceramic. And then it signs over that. So the wallet basically signs, giving the session key access to write on behalf of the did PKH to this resource. Now the application has the session key, and it kind of packages the signature and the message that was signed from the wallet into an IPLE format called Cacao. And every time the application wants to update this resource, basically makes JWS signatures, store that as Dag Jose, and includes a reference to basically includes the CID as part of like the signature payload of the Cacao as an invocation. So now like the session key invokes the capability it got from the PKH and is able to update the resource on behalf of the wallet essentially. So this allows us to like make delegations from like existing wallets and existing public key infrastructure. You can of course also create an event streaming in Ceramic that only relies on a DID key, and the resource is actually controlled by directly a DID key. It kind of depends on like what sort of application you want to deploy. So like if you have a server-side application, you don't really need like a wallet and all that infrastructure for users. You can just use a public-private key pair and use the DID key method. So there depends a little bit on how you would approach things. But for users, this is really neat. Cool. Yeah, and there's also work happening to kind of align the Cacao format and the Cacao support for like signing with Ethereum and potentially like other on-chain capabilities with the work done by UCAN. So kind of like harmonizing those standards because they kind of achieve somewhat different goals, but they have similar goals, but they do different things right now, or they have different capabilities, no pun intended, right now. Cool. And then, so what are kind of the use cases for event streams? So one that I already talked about, because we are building a database on top of this, is of course you can use event streams for databases. And what's neat about this is that you don't need to build like a mapping like one-to-one, like one type of event stream to a database. You can actually have event streams and then build different sorts of databases on top of it. So you can specialize per use case. Someone might want to build like a large scale like application database. Someone might want to build like a privacy preserving database that encrypts all the data. Someone wants to maybe like build like a local first database that doesn't really like care about the global state, but kind of, or you want something that works in both cases, like both local and like a global database that's like optimized for both. And the event streams are kind of agnostic as to like what sort of indexes and what sort of databases you build on top. And since we leverage event streams, we can kind of like have different consistency models as well. Like I might want to have like, I plug into some event streams and build my own database locally on my machine, and other people do the same. Or I might want to build like a database that actually leverage a blockchain to like ingest events from event streams and build consensus of like what we observed in these event streams and build an index. And so we have like consensus over that index that's more trustless. And you can kind of like mix and match these approaches, which is what's really cool when using event streams for databases. I think what is probably more interesting for this group is like using event streams for compute. So we can think of like an event stream as like sort of like a formal glue between different compute stages in a data pipeline. And so imagine that you have like someone produces some data and outputs that into an event stream and signs it. And now, okay, I trust this author of that data. I'm going to actually plug into that, run some computation on top of that or the set of event streams, output my result of my computation into a new event stream, and then maybe like do an extra step after that and do the same sort of thing. Or you might actually want to have these sort of open-ended pipelines where I build a pipeline based on like some events and then some computation, some events, and I achieve a particular goal. But then someone else plugs into like halfway through my pipeline and does something differently. And so I think that this possibility of having these kind of open and composable data pipelines are really interesting. And of course, like this ends us up in like some sort of like semi-trusted inputs and outputs, where since we have this event stream, we know that like, okay, whoever produced this computation signed the output. And if you trust that actor, maybe you can just consume that. Or if you're like suspicious, maybe like you want to have a system where you have like 5 different nodes or 5 different organizations that run the same computation and produce the output. And if it's the same, you can kind of trust it. Or you actually have like a consensus system around it. But you can kind of like mix and match, which is kind of cool. And so if you were to build this sort of like system on top of Ceramic event streams, Ceramic wouldn't really care about like how you define compute jobs and how they're executed. I know there's like, because the only thing Ceramic would care about is you produce an event stream that the signatures are correctly produced, and it's up to you to how you interpret those events. And yeah, I know that there's like a bunch of different interesting projects in like the IPFS Filecoin space, where I think there's like this project trying to build a IPLI, I think it was called, like the linked invocation. I don't know if there's anything public about that, but that was talked about during the IPFS thing. I know Block Science is building this CAT thing, which is like content addressable transformers. And there's probably like a bunch more different examples that I'm not aware of. And it would be cool if we can kind of plug this thing into these event streams and kind of like sort of mix and match these sort of different approaches to computation. And yeah, so my question to this group is there like an appetite to standardize around some of these things? Like, do we want to standardize how we do an event log data structure and how we verify signatures, how we do DID authentication, authorization, and how we do like timestamps through anchors? I think, and maybe like we want to standardize around how we synchronize these event streams in a peer-to-peer manner. But I think like only standardizing around like, a data structure would be really interesting, because then we can at least have a standardized way of validating things across the ecosystem. So yeah, that's the question I want to pose to this community. And if there's interest, we'd be happy to like maybe make a first proposal of like what this sort of thing could look like. If this is not interesting, then but yeah, that's essentially it from my end. Happy to talk about this or answer any questions.
Thank you so much, Joel. I've got a couple of questions, but I'll just open up the rest of the audience in case anybody else has questions they want to raise first. Well, Joel, for what it's worth, I know the Fission folks are not here today, but they're very actively pushing the DID standard forward as well. So I think other folks in the community will also have strong opinions. I'll take a couple notes on the standards component that you raised, because I think that's a great idea. I love the idea of you guys are building it out. You guys can be the first. And if other folks want to, collaborate on that, all the better. If not, at least we have a first implementation. And I thought it was really interesting how you were sharing, to go back to the notes here, the different permutations of event streams, and do you have any indication about like the data sizes that would be ideal for event streams, and are they limited to one node processing the data streams, or is it even large big data sets as well?
Yeah, currently how Ceramic is designed is that Ceramic Network doesn't really care about how the event streams are replicated. It's kind of like up to your node to decide, hey, I want to replicate this particular event stream. And so if you want to build like a really large event stream that has huge chunks of data, that's fine. Or you maybe just want to build an event stream that has references to CIDs that you could retrieve off Filecoin, and you have the data integrity stored in Ceramic, or like the kind of not the data integrity, but that's by the CID, but like the integrity of like the process of like how different pieces of data was processed and attested to over time.
No, I appreciate it. That's a good context, because metadata around data stored in Filecoin is, and IPFS has become a hot issue as well. So I mean, this lends some structure there.
Yeah, I'd like to plus one on the creating the general standards, and yeah, we don't have everyone here, but the extent to which we can start getting those documents, onto our pages for people to discuss, I think would be amazing. And Wes is exactly right. First person to propose something. This is a lowercase s standard. I want to make clear, like, just up to us to figure out how to, produce it, and anyone who wants to use it can, and anyone who doesn't have to. But the extent to which, we can have things go across platforms, I think is incredibly powerful, and certainly something that I think a lot of people would be excited about.
Very good. All right, Joel, thank you so much for the overview. Appreciate that. That was tremendous. So moving on to the second half of the session, David, I can hand it over to you if you'd like to give us a brief intro of Bacalhau.
I'm actually just going to hand it to Luke.
Okay, great.
There we go.
Cool. So hi, folks. I will share my screen. The first challenge is sharing the correct screen, because sometimes I share the wrong screen and then I do the whole presentation and someone's just looking at my inbox. So hopefully you can see some slides. Can everyone see some slides?
Yes, looks good.
Okay, great. Cool. So hi, everyone. I'm Luke. I'm here with Kai, who we are the tech co-leads on the Bacalhau project. And we also work with David and Wes on this project too. Just kind of by way of setting some context, we are working on a compute over data project, but we also have this kind of dual mandate. So we have two jobs, basically. We have the job of building a working distributed compute network that will be valuable for users, a bit like IPFS for compute. And we also have the job of making this working group successful and helping the people in this working group, the teams in this working group, to be more successful by building blocks for you, finding ways to collaborate and build common libraries or common standards, and by splitting out working code from whatever we're building that can be shared in the community. And I wanted to share a little bit of sort of history here. So Dave and I have some history together. Dave was the product manager for Kubernetes at Google in the early Kubernetes days. And that's where we met, because we were both working on trying to make Kubernetes easier to install. And the situation then was that there were many different projects to try and make it easy to install Kubernetes. And there was a great deal of fragmentation amongst those projects and a lot of overlap between those projects. A lot of them were doing a lot of the same things, and it kind of sucked for everyone because it was more complex than it needed to be. And so what we did was we started this working group called SIG Cluster Lifecycle, and we built a reference implementation, which was kubeadm for installing Kubernetes. But we also made sure that kubeadm could be vendored into other projects and was providing building blocks for other projects. And we had great success with this because within a few weeks and months of kubeadm going out there, we had KubeSpray, Kops, Minikube, Kind, lots of the other Kubernetes installer projects started adopting the building blocks that, that we put out there. And therefore, they were able to spend more time on their differentiated features and became more successful as installer projects. So that's basically, we're here to do that again in the COD, in the compute over data Web3 space. So that's kind of what we're hoping to achieve. So with that, I want to talk a little bit about what we've got now. And as you look at this, if you're working on a project in this space, if you're here in the room now, or if you're watching the recording later, have a think about whether there's anything in this that's useful to you. And if there is, then please ask us to split it out, and we'll split it out into a reusable component that you can use so that you have to maintain less code. So we have this peer-to-peer compute network that interacts primarily with IPFS, supports users showing up using a CLI to submit jobs that can either be Docker jobs, so they can bring their own Docker image, or they can just bring a Python script and we'll run Python inside WASM for them. The reason for that is that we are going down a path of determinism, which is easier to achieve in WASM. And I'll talk about that more in a minute. The determinism is in order to enable verifiability, which enables us to start to have some confidence in the results. We support concurrency, so you can say how many times you want to run your job. And so you can say concurrency equals 3, and then 3 nodes in the network will pick it up. You can also, just recently we added support for sharding. So you can say, I've got a job that has 10,000 files in it. I need to resize 10,000 images. I want to do that in a batch size of 100. And you just mention a glob pattern of like star.jpg, batch size equals 100 in your command. And then it will get run across 10 nodes in parallel, and the results get reassembled automatically. We support reading from IPFS, obviously. We also support reading from HTTP because there's an awful lot of data sets available over HTTP on the internet. So this can also act as a bridge, as a way for people to get data into IPFS by reading it from HTTP, processing it, and writing the results to IPFS. And right now we also write to IPFS. And we've got this thing scaling up to 750 nodes with lots of performance work ongoing to make things fast at 750, 1K, 10K. We're working on scaling it up to tens of thousands of nodes operating on petabytes of data. So that's kind of where we are today. I can show you a quick demo. If you please pray to the demo gods. We just got this working a few hours ago. So what we have here is, I'm going to do a little bit of work locally. So imagine I am working on processing video data, and I've got some video files on my local machine, and I've also got a great deal more video data on IPFS that is more data than I can fit on my local machine. And so here we have the local data, and here we have kind of, you have to use your imagination a little bit, but imagine that there was tons and tons and tons of data in this IPFS CID that was more than I could fit on my physical machine. So the first thing we're going to do, well, I'll actually show you what the video is and then show you what the workload is. So I'm going to look at the video. It's just some nice footage of looking at a Gothic building. And then there's some other footage that we're gonna use. And what we want to do is we want to apply a funky matrix style overlay on the top of this video. So I'm going to do that locally by running a Docker command. And this is going to use ffmpeg inside a Docker container. And this is just operating on this, literally this local file that I have on my computer. And it's processing it and outputting the processed video data in my outputs directory that I have here. I can show you exactly what that job was if I scroll up enough. So we did a Docker run. We mounted the inputs directory and the outputs directory, and we ran this video resize example container image, and we just ran a shell script inside it and pointed it to the inputs directory and the outputs directory. So that's how you run things in Docker normally. So it's finished. And so we can see what this looks like. And there we have it, this sort of funky matrix style text that's being overlaid over the image, over the video. Now, we're probably not going to win any awards for our video work, but this will kind of serve to demonstrate the point, I hope. So I'm now going to export this CID. Now, remember, this CID points to this data, which, for the sake of argument, imagine this is more data than you could process on your local machine. So I'm going to show you two things. The first thing is I'm going to show you just running that same container image on the Bacalhau network. So, and I'm going to time it so you can see how long it takes. So we're doing, instead of Docker run, we're doing Bacalhau Docker run. So we've made the Docker run command in Bacalhau very similar to the one that you get from Docker, so that people are familiar with it. And oh yeah, just quickly, I want to show you what's actually happening on the nodes. So this is 3 nodes on our production network. One of those nodes has picked up that job and is running it, and it's finished. So in 31 seconds, it has processed those 3 files. So yeah, just to show you the command in a bit more detail, we're mounting the CID as an input volume, and Bacalhau will handle reading the data in from IPFS. And then we can specify you get 2 CPUs for gigabyte of memory. And then we can say, please wait until the job finishes, which is why it actually waited. This command blocked until the command finished. And then you can run Bacalhau get on the job ID, and we will see that we can see the results of that. Excuse me. So we can see now that we've got processed video footage from the Bacalhau network. Okay, so that's pretty cool. And you can also see if there was any errors or any messages on standard out, those also get written out to these files here. So I'm going to clean up from that run. And then I'm also going to show you what you can do when you use sharding. And so sharding is about parallelizing the work across multiple machines on the network. And so what we're doing here, and actually I need to show you this quite quickly because it's so fast, is that the work got spread out across multiple of the nodes on the network. You can see this middle node picked up one of the jobs, and the third node here picked up 2 of the jobs. It's a bit random at the moment which nodes pick up which jobs, but and you can see we did the work 10 seconds faster than we did when we just ran it one after the other. So that's pretty cool. We can slash the runtime of our work by parallelizing it across the network. And now if we do Bacalhau get on that job ID, then you can see this time we had 3 shards. We've got shard 0 and shard 2 and shard 1 showing up. And so you get separate exit codes and standard out and standard error from all of them. But then inside volumes, you get the same data reassembled in the output volume directly. So yeah, that's the demo. That's kind of what we have now with Bacalhau. And yeah, I'll if you've got questions, please hold on to them. I'll take questions at the end. So I'll just kind of blast through our roadmap and talk about what we're going to do next. And like I said, so as you're looking through the roadmap, if there are things here that are interesting that you'd like us to split out into separate projects, then please come and tell us. Because we want to do that to make the whole community successful. So the current roadmap looks like this. I've got a few slides here for each year half. So I've got till the end of this year, first half of next year, second half of next year, and then the first half of 2024. And notice that in our roadmap, we have these explicit goals, like I said, for making the Compute Over Data Working Group successful. So we want to find partners who can use our code or integrate with us in a meaningful way. And we don't know how much engineering effort each of those integration efforts will take, but we are resourced to do that. We are also working on making users successful. So you'll see that throughout the roadmap is that we have targets on that. And then you can also see the kind of feature work and that we're adding. So there's a big focus at the moment on performance, getting performance down to seconds of job execution in 1,000 node networks. We're not far from that now, but there's almost always more performance work to do. We're also working on a Filecoin publisher so that you can write the outputs of your jobs to Filecoin as well as IPFS. Then we're going to work on Byzantine fault tolerance, so making it so that even if 10% of the nodes in the network are lying, then you'll still be able to get useful work done. And one of the first ways that we're going to do that is to start verifying the outputs. So if you, like I mentioned earlier, with the deterministic execution mode in WASM, you will be able to start assuming that if multiple nodes came to the same result, then, well, either they all did the work correctly or they're all lying. Yeah, being able to hash the outputs of deterministic jobs is kind of step one in our approach to addressing Byzantine fault tolerance. We're also looking to make users successful. Then after that, we are adding support for DAG execution. So right now we have single jobs and we have sharded jobs, and those are kind of two of the building blocks that you need to build a more generic DAG execution engine. So we're working on that. We're looking at whether to integrate with existing DAG execution engines versus building our own. Ideally, we don't want to reinvent the wheel. So if we can integrate with something like Airflow, for example, then we might do that, but that's all TBD. We haven't designed that yet. And then, of course, as we go through this, we're interested in finding ways to factor out what we've done and help and use it to help other participants in the working group. Then we are upping our game on Byzantine fault tolerance towards the end of the year. We're looking towards making more users successful as well, of course. In January next year, we might tackle non-determinism, which is how do you verify? So you can currently run non-deterministic jobs on the network, but obviously you can't. It's harder to verify non-deterministic jobs than it is deterministic jobs. So we built a prototype earlier on in the project of how you could verify non-deterministic jobs. I won't dive too much into that now, but if you have questions, please ask. Then more focus on working group successes and user successes. And then we're going to probably around March next year, pick up prototyping a verification protocol around Bacalhau. So the, let me just pull up some notes here. The verification protocol will help us to move towards being able to build systems like this that eventually interact with incentives. And so the verification protocol, for example, we have a draft of right now that we, for example, can have nodes randomly check the work that nodes do. And then if the nodes are found to be lying, then start to, for example, slash those nodes in some way. And then that prototyping of that protocol, which we have a draft of in the wiki, will allow us to start kind of testing those ideas. And that will lead towards being able to connect the network to a smart contract. So we have this large piece of work in April through June next year around integrating with a smart contract. And one of the ideas is that our entire transport and scheduler layer, which currently is just a custom implementation on top of Gossip Sub on libp2p, would become replaced with, for example, an FVM contract. So that FVM contract would then be responsible for implementing the verification protocol. And then around that time, we're looking at, so just after we start work on the smart contract, we're also going to spin up an effort around formal verification. Let me just pull up some notes on this as well. Sorry, I should have had these already. But basically, let me see, sorry. Here it is. So, so the formal verification, we're looking at tools like Glow, Daphne, Coq, and Y3 as ways to encode the behavior of the verification protocol in a formal system that we can mathematically prove things about. And the goal of that effort is to make it is basically to eliminate bugs in the protocol, like earlier than finding them because we get hacked. And so that will be quite a big effort, but we believe it will be worthwhile, and we think it's very interesting. I think I've worked previously on formal verification of some network algorithms where we actually found novel attacks against established protocols by using formal verification. So I think that's an area that is super interesting in the space, honestly. So excited to potentially spin up an effort around that. And then I see basically the big challenge that I see with moving to a smart contract implementation of the transport and the scheduler layer in the system is efficiency. So once we have all of the kind of scheduling and metadata around this job execution happening on chain, then we expect that will initially dramatically reduce the performance of the system. And so we've got like a whole half a year dedicated to getting that back up to scratch in parallel with formal verification, all the while making users successful and helping split out work that we're doing. And then come October, we plan to build a plugin system. The plugin system relates to the non-deterministic execution that I mentioned earlier. We're also then going to look at a reputation system, which is kind of using the outputs from the smart contract and the verification protocol to make basically a public dashboard of which compute nodes are reputable and which ones are not, based on which ones have been deemed to be publishing good results and which ones are not. And then for the following half of 2024, looking at incentive models, developer experience. And then we've also heard a lot of demand for secrecy. So currently the network is fully public, and so both the data and the compute has to be fully public. Now, this is obviously problematic if you have private data or you do not want to make your code open source effectively by publishing it on the network. So we're really interested in talking to other working group participants who are already addressing secrecy and potentially partnering with them because we see that as a very difficult problem to solve, frankly. Then more user success, scaling up the number of users, scaling up the number of working group partners who we have, building on the foundations that we're laying, hopefully. Then finally, the very last thing on the roadmap in the foreseeable future is extending the compute network to also work with long-running services like microservices or API servers, where they are interacting, responding to network requests rather than just doing batch jobs over data. And that's fundamentally harder because how do you verify the result of someone, of a compute node that's dealing with an arbitrary API request? Because the profile of that execution is going to be different depending on what API requests come in. So there's a whole interesting area of work there. But I'll stop to make sure that we have time for Q&A and discussion here. I'd love to hear from folks on the call or in the recording afterwards. Are there any parts of what we have already that you think might be candidate independent building blocks? As in, what should we split out first? Is there anything on the roadmap that people would like to collaborate on? We'd love to work with other teams. And is there anything you think that we should work on that we don't have on our roadmap today? Because we're here to serve the working group. So yeah, thank you. I'd love to hear answers to those questions or any other questions that people have.
Well, I'll give everybody else a minute to chime in if they have questions. I will also add, both Luke, for these questions and also the ones that Joel raised, we are going to be launching a discourse server soon for the community. So at the very least, even for folks that can't join live, we'll mark these up as sort of our first issues for discussion purposes and try to funnel folks there as well. But I'll just pause before you. Does anybody else have any questions? Okay. All right. Well, we'll have the content up on YouTube here shortly, so other folks can view it. A lot of folks weren't able to join on the call today live, but Luke, Joel, I'll just pause to see if you guys have anything else.
Yeah, if Joel is still on the call, I wanted to say I really enjoyed your presentation. Thank you. As you can see from kind of what we're working on, the identity standard stuff that you mentioned is not directly relevant to our goals, but it sounds like a very useful thing to have. Yeah, I don't know, maybe you have some thoughts on whether there's intersections between our work that could be helpful.
Yeah, I mean, the stuff you presented on your roadmap is like very wide and a lot of like open problems. So I can't like really speak to like exactly how it will fit in, but like we basically use the DID standard basically because like it's like a neat format to represent different sort of accounts. And so you can use the public private key pair that signs the output of the data, or you can have something more sophisticated with this blockchain wallet and object capability thing. And all of it kind of like fits in this DID package. So I think like if you ever have like a thing that needs more than just like, okay, I have a compute job that I run and here's a signature over it and I put it on the blockchain, then that might be interesting. Or yeah, I guess like, so I guess a question back to you is like, as you imagine Bacalhau right now, is it like a fully kind of just like incentivized compute network? Or do you imagine like as people build different like compute pipelines on top of it, you actually have some people that run like a centralized services just puts inputs, outputs in there, and then maybe there's part of the pipeline that's like more distributed and more verified. Or like, how do will there be like that sort of like dynamic thing in there, or do you think it's like one sort of system?
I think, yeah, I think we don't really know yet. I think it could go either way. I think if we develop the building blocks, if we're able to help develop the building blocks for like 10 different projects to be successful, then I think that will be deemed a success. And at the same time, we're also going to be guided by what our users are asking for and what the storage providers who we want to integrate with are asking for and things like that. So yeah, not a direct answer, I'm afraid, but we'll see.
Yeah, no,
yeah. Go ahead.
No, that makes sense. And like, I'm interested to see, like, you know, from a very, very abstract perspective, like, how can we, because different people are building different sort, like you're building one compute project, there are other people building like different sorts of compute projects. I think that the thing that block science is doing with like having just what they call CAT, content addressable transformers. It's also interesting. There's like do sort of the same thing: input CAD, output CAD, code CAD, and run some computation. And like the ability to take these different sorts of compute systems and like plug them together because they might be good at different things.
Yeah,
and that's where I think it's like wondering, like, can we standardize around some way where we like, this is how we shuffle data between the systems?
That would be very interesting. I think that's a thread that we should pull on and work on together. And also on the DID thing, I think it might be interesting to see how whether identity for both users submitting the jobs and also for the compute providers is useful in that world. Sorry, go ahead, Kai.
I was just going to say, when we get to the DAG story, that's an opportunity for Bacalhau to be one stage of a DAG. So when we start to think, what is a DAG? Like bringing various systems together, because if I say consume an input from IPFS and write the output to IPFS, and then I tell another system, hey, your input is here, I just wrote it, then we start to have, like, as in the pipeline between these various systems can be the storage of the output and then reading from that input, and there's various ways that we can integrate like that. And yeah, I think it's a compelling picture to say there's lots of different compute projects out there, each would be good at a various stage of the pipeline, is a very strong statement. I like it.
Yeah, and just a quick note on the kind of DID thing, like, I don't see DIDs in the abstract form as identity. I see them as like a cryptographic identifier. And so it's like a mapping from like a random letter string to some sort of public keys. So I don't view it as like we're building this as like an identity piece in the event log. You can use it for identity, but it's not kind of what it is at its core.
Got it. Okay.
I know we are out of time, and before everyone departs, I just wanted to say we will be circulating. Please do mark down on your calendar. Sorry to cut it off the conversation. It's just we're out of time, and I do want to cover this one item. November 2nd and 3rd in Lisbon is going to be the Compute Over Data Summit. I will be sending around a. We're trying to build the schedule right now. It is supposed to be collaborative. I would love to have lots of people talk, you know, over the course of the day, talk about your projects, talk about things that are interesting to you, and then work on some tracks, hallway tracks or not hallway, but unconference or other tracks where we can collaborate on particular items like specs and things like that. So please keep your eye out for that, and do jump in the Compute Over Data working group Slack to continue the conversations. I just don't want to, I mean, we could continue to talk now to be clear, but I just didn't want to miss out on the opportunity for everyone to collaborate.
Sounds good.
Very good. All right, we'll go ahead and wrap for today. Thank you so much, Joel and Luke. Excellent content today, guys.
Yeah, nice to meet you. And thanks, everyone.
Thanks all. Bye.
Take care. Bye-bye.
Bye, guys.